Okay, before we start looking at energy bar graphs, I wanted to review energy pie charts really quickly. This is number 3 from 1B that you whiteboarded yesterday. We have this ball that goes up in the air and kind of comes back down. And all it says was to draw the velocity arrows next to each position and then draw the energy pie charts. Well, there's lots of room for interpretation on these. First of all, you have to define what your system is. And I'm going to say my system is the ball Earth. Because if you think about it, why is it that the ball is slowing down here? It is slowing down as it goes up and then speeds up coming down. It's because the Earth is exerting a pull on it. Well, the ball is also exerting a pull on the Earth. So we really have to look at both of these objects together. So my assumption that I'm going to say here is that we're going to assume that there is air resistance. So it's going to be somewhat practical. But at the same time, I'm going to say that there's no loss of energy. Well, you might think, well, that's kind of crazy. But if you think about it, this ball goes up and goes down. It happens pretty quickly. Yeah, there probably would be some loss of energy, but it probably wouldn't be as much as you think, since it happens so quickly. So if I'm looking at part A here, let's say I define my ground to be down here somewhere. At that position, it does have gravitational potential energy, and since it has speed, it has kinetic energy. At B, it also has speed, and it has a height now, even higher, so it's going to have even more gravitational energy. The speed's less, so it's less kinetic energy. But since there's air resistance, there's going to be a dissipative energy there. Again, those particles are moving around kind of fast. At C, there's still a speed energy, but it's less kinetic energy. Has more gravitational energy, and it has a little bit more dissipative energy, although you can't tell here. Every one of these pies should look like they're the same size, because they don't have any energy going out of it or into it. At D, D is exactly half the height of C, so I'm going to say at D, the energy for the gravitational energy should look like about half of what it was over here. I'm hoping it looks like it's about half. The dissipative energy increased and the kinetic energy increased. And then finally at E, the dissipative energy increased a little bit more than over here. The gravitational energy should look the same as the gravitational energy over here at this position. The kinetic energy isn't quite as much as it used to be over here because now the dissipative energy is taken up some. So this is one way to do it. This isn't the only right way. For instance, I could say that there would be a loss of energy. So for every one of the dissipative energy, I could have a Q coming out, a heating. And so my overall circle is decreasing in size. I could say this is some fancy place where there's no air resistance, and so I wouldn't even have a dissipative energy. And then it becomes even easier. All the pies would be the same size. I just have gravitational energy and kinetic energy. So this is one way of doing it. However, that height level of 0 is totally arbitrary. I could have set 0 to be anywhere. For instance, I could have set my reference height to be 0 here, in which case that means the gravitational energy here is negative. Here it's even more negative, and these two have the same, and it's the most negative. But how do I draw negative over here? I can't. So that's why I need to come up with some new graphical representation. And what we're going to look at is energy bar charts. Now we're going to look at energy bar charts. I'm only going to look at position A, that was at the beginning of the parabola, and at position D, which is about half the height. Let's set the reference level, so let me redraw that parabola. Here was A, kind of right here. And D was kind of right here. I'm just going to look at these two positions. At A, we said that it had kinetic energy, but we also said it had gravitational energy. Let's set the reference height level to be here. I could. In other words, let's say the height there is equal to 0. In which case, it would have no gravitational energy. It would only have kinetic energy. So this is how an energy bar chart would look like. In this case, if I set my gravitational energy to be 0 at that height, I would only have a kinetic energy, and let's say I'm just going to make it 4 bars high. Okay. Then over at, it doesn't have any gravitational, it doesn't have any elastic. Then over at position D, it's going to have gravitational energy now, and it's going to have kinetic energy. It won't have any elastic energy, and we also said it had some dissipative energy. The kinetic energy, first of all, let's assume, again, there's no loss of energy from the system. The kinetic energy would be about half of what it was a day. Actually, it's going to be, let's see. Yeah, it's going to be a little bit more than half. So maybe something kind of up in here somewhere. Then there's going to be some gravitational energy and some dissipative energy as well. Now, whether you know that it's more than half or less than half, that doesn't really matter. I think it's more than half. How's that? Okay. Here's the point. If this was 4 bars over here, 1, 2, 3, 4, and I don't have any energy leaving my system, there has to be a total of 4 bars here. And right now I've got 1, 2, maybe about 2 1/3. So let's say that I have the dissipative energy to be equal to 2/3. So then what does the gravitational energy have to be? Well, if it has to be equal to 4 altogether, so this is going to be 2 1/3 plus 2/3 more, that'd be 3. The gravitational energy has got to be 1 bar. Okay. My system in this case again was the ball Earth. And as far as the flow, I don't have any energy flowing into or out of. There was no heating or anything else. That's the way I defined it. However, let's say that back over here on my energy pie chart, I did have some energy leaving as heat. Okay. In that case, I would still have 4 bars, let's say, here for kinetic energy. But over here, this wouldn't in total be 4 bars. It would have to be less because I have some energy leaving. And probably what's going to happen is my gravitational will probably be the same, the dissipative would probably be the same. It's probably going to be the kinetic energy that's less. So maybe something like that. Now if you add it together, I got 1 1/2 plus another 1, that's 2 1/2 plus 2/3. So we have something that's a little bit more than 3 instead of 4. So we've kind of lost almost a whole unit of energy. Well, how did we lose that energy? That was through heating. Here. And again, the system was the same as the ball Earth. So this is a energy bar chart. What's kind of cool about it is that with energy bar charts, you can actually get negative bars where you can't get that with the pie charts. For instance, we didn't have to set this as the reference height. We could have set up here as the reference height of 0, h equals 0. What's kind of cool about that then is it would have a kinetic energy. It would also have a gravitational energy, and that would be negative. So let's imagine that for a second. Let's say it was negative 4 bars. Again, I'm just totally making this up. It's arbitrary. So here's 1, here's 2, here's 3, here's 4. So here's my negative gravitational energy. Let's again assume there's no losses of energy. So what is my total over here? Well, I've got positive 4, negative 4, I've got a total of 0. So that's what it has to be over here. So at D, I would have kinetic energy, and that kinetic energy is probably going to be around half of what it was at A. Probably a little bit more, maybe a little bit less. Let's see. Let's say it's a little bit more. So again, maybe 2 1/3. Well, hopefully you can see that the gravitational energy at D is negative again. Of course, it's not -4, but it's going to be some negative amount. The dissipative energy is still going to be positive. So right now I've got 1, 2, and I've got a third. This is 2/3, so I've got a positive 3 altogether. So how much does the gravitational energy have to be? Well, if you think about it, I have to get 0 total, right? This is 4, that's -4. Well, if I got positive 3, then this has to be -3. Which kind of makes sense, because it's not as far below the line as A is. So that's what you're doing on worksheet 2.